Hey everyone, my name is Cong from University of Waterloo. Thank you everyone for staying up to the last talk, and I hope everyone have a good time here. I personally have been camping in the mountains for the good part of this week. I certainly have fun here. Okay, so this talk is about virtualizing continuations, and you need to understand what effect handlers and multishot continuations are to understand this talk. And I will introduce these concepts after I give you the big picture of this work. So effect handlers and multishot continuations are powerful language features, and they are compiled using distinctive techniques. Effect handler is compiled usually using stack switching, and the multishot continuations is compiled using stack copying. And these two techniques are in conflict with each other. And in this work, we introduce a novel technique called virtual continuation to resolve this conflict. Now, coming back to the background. Let me introduce the concept using the example of n queens. N queens is a problem that asks you to place n queens on a board of size n times n, so that no two queens are on the same row, same column, or same diagonal lines. And this is a typical implementation of n queens. You have a function safe that checks whether a placement on a row is compatible with a partial solution. You have a recursive function place taking in the size of the board, the row that you're currently trying to place the queen on, and the partial solution. And inside the place, you have a for loop that iteratively tries different placement on that row. And for each try, you check whether it's safe or not. If it's not safe, you continue to the next loop. And if it's safe, you recursively call place to try on the next row. This is the same function, just have this variable name shortened for the sake of space. And I'm going to show you a second flavor of the implementation. In this implementation, I use effect handlers. And let's look at the difference between these two versions. Instead of having an explicit for loop, I perform a choose effect given a list of choices. And instead of, say, continue when an option is not safe, I perform a fail effect. So in a sense, this version abstracts away search strategy. And where is search strategy specified? Well, they're specified in a handler somewhere up the call chain. And in this example, n queens is a function that installs a handler inside the body. And inside the handler with expression, we see an invocation of place. Now, when a callee performs a choose effect, the control will be transferred to the handler here. And we can see the familiar for loop inside the handler. Raising an effect and transfer the control to handler is not so much different than calling a function and having the control transferred to the callee. The magic of effect handler comes from this extra parameter k, which every handler takes in. K is the continuation from the place that raised effect to the place where the handler is installed. In a program, the k can be resumed at any time. And when that happens, control will come back to the place where effect was raised, carrying choice as an argument. Effect handler gives you a way to do this kind of non-local control transfers back and forth. And it is a very powerful language feature. It allows you to write very modular code for some algorithms, particularly the one involves search and backtracking. In this example, we see that the continuation is used inside the loop, and it's used multiple times. This is called multishot continuation. It is challenging and to implement multishot continuation efficiently and correctly. Now, let me give you a short digression to the semantics of effect handlers. Traditionally, effect handlers are dynamically scoped. Think of exception in Java. When the exception is raised, the closest enclosing handler at the runtime is used. I come from a camp where we advocate for lexically scoped handlers. The semantic says that when control enters a handler's scope, a handler capability is generated. It is passed down the stack and used at the raise side. This semantics is commonly found in research languages such as effect and lexa, and I heard that Oxcaml is experimenting with this semantics too. So to give you a flavor of lexical handlers, let me show you how the program will look like with lexical handlers. For n queens, we need to parameterize or add a binder for a capability variable to every handle with expression. And we need to pass this capability variable to any place that could raise effect. Furthermore, we also need to parameterize every function that could raise effect with an extra capability parameter. And every perform expression now needs to take in a capability as well. Effect handlers are a unifying control flow mechanism. They introduce first-class continuation into a language, and continuation can be single-shot or multi-shot. Multi-shot continuations are very expressive, as we've seen from the earlier example. Now, effect handlers, as I said before, is compiled using stack switching, and multi-shot continuations are compiled using stack copying, and these are in conflict, and I'll show you where they are in conflict. I'm going to show you how these two techniques work. Here, again, it's the same function, n queens and place. The orange stack represents the activation frame for n queens, and the green stack represents activation frames for place. When we install a handler, the runtime allocates a new stack and start the computation on that new stack. The runtime also takes the address at the bottom of the stack, represented by this pink triangle, and use that to serve as the reference or capability for the handler, and pass that reference down to the call chain. So now the execution is at a place where we're about to raise the choose effect. What happens is that we follow the pink pointer to the place where handler is installed, and we simply switch stack pointer to the place where handler is installed, like this. And now control comes to the handler in a place where we are about to resume the continuation. Similarly, we simply switch the stack pointer to the green stack. And that's where the name comes from. We model the capturing and resuming of continuation by switching the stacks. Something that I did not mention in the prior slides is that this use of continuation is actually in a multi-shot fashion. And to be able to resume a continuation in a multi-shot, we need to copy the stack, because otherwise the stack could be destructively modified. And that's what we'll do here. When we resume continuation, we first copy the green stack, and then we switch the stack pointer to the copy. And you might already notice a problem here. By copying the stack, we're also copying the reference to a stale pointer to the handler. And the semantics really says that this pointer should be pointing to the copy of the handler in the green stack. So here's the challenge. The stack switching technique refers to handlers using stack addresses, which is incompatible with stack copying. To solve this problem, we borrowed the idea of virtual memory management. In a virtual memory system, all processes have an illusion that they own the entire memory space. And whenever an address is used, it goes through the translation of MMU and eventually goes to the physical memory. And if you squint your eyes hard enough, you can see a similarity between processes and continuations. Whenever a stack pointer is used in a continuation, we really wish to have an indirection mechanism that point this pointer to the right copy or the local memory region in a continuation. And that's what we did. We implement a runtime library called SMMU that carries out this redirection. To note that we still have the virtual memory provided by the operating system, but because it's transparent to our design, I'm not going to talk about it in the rest of slides. Now let's look at how virtual continuation works. The key idea is that we partition the entire memory space into zones, and every address now is a virtual address. The top portion of an address is what we call zone number. Middle portion we call handler ID, and the lower portion are stack offset. As you can see from the diagram here, we have two stacks. They all live in zone 0, so they have the same zone number. And because there are different stacks, they have different handler ID. Now, when we copy a stack, this is important, we bump the zone number and copy it into a higher zone. And crucially, we copy it into the same relative offset inside the zone. This ensures that the same copy of the stack will have the same handler ID in their addresses. Now, after we lay out the memory this way, let's see how an address translation works. Say that right now, we're raising to a handler installed at 0, 1, 0. The runtime takes over the control, and it looks at the current stack pointer and determines that we're currently in zone 1. Runtime simply updates the virtual memory by replacing the zone number to the current zone. And we get the address 110, which is exactly the right copy that we need. In our system, a stack pointer's upper part is meaningless. It is contextualized at runtime according to the current execution point. Now, we've only covered a simple case in this example. In general, the target handler can be in a different zone. I'm going to show you a more complicated example. We have a yellow stack, a green stack, and a blue stack. And the blue stack captures an address from the green stack. Now, let's copy the blue stack and raise to the address 0, 1, 0. This time, if we naively update the zone number to the current zone, we get address 110, which doesn't exist. Instead, for each translation, the runtime performs a zone walk. We first look at the virtual address and grab the target handler ID 1. And we look at the stack pointer, grab the initial zone, and the runtime remembers these two values. And then we start a zone walk. At every zone, we ask a question. Is there a handler with ID 1 in this zone? And how can we check? Well, it's a difficult question because at that address, you could have data or you could have garbage. We perform a clever trick. We look at the first handler in the zone. We grab its handler ID and compare it with our target handler ID. Because our target handler ID is smaller, we know that the target handler is not in the zone. But why? Our runtime maintains two important invariants for this presence check to work. First, handler IDs are assigned monotonically. For example, in these 3 nested handlers, when they're reduced at runtime, they will be given handler ID in increasing order, like 0, 1, 2. Second, handler capabilities are scoped lexically, which is dictated by our lexical handler semantics. Now, installing a handler corresponds to the start of the lifetime of a continuation. Due to lexical scoping, this continuation can only reach to handlers that have already been allocated with smaller IDs. And handlers within this continuation are allocated later with greater IDs. Therefore, every handler demarcates the inside and outside continuations, with inside continuation having greater IDs and outside continuation having smaller IDs. Now, coming back to the illustration. When we compare the edge of the zone, which corresponds to the boundary of continuation, we are sure that if the target handler is smaller than the first handler in the zone, the handler doesn't exist. Therefore, we continue the zone walk. Now we reach zone 0, and we look at the first handler, which has handler ID 1, comparing with, 0, and comparing with 1, we find that our target handler is greater. So we're sure that the handler is within zone 0. And the reason we prove the correctness of it in the paper. So coming back to our virtual address, right? We know that our target handler is in zone 0, so we remove the zone number and replace it with the correct zone number. And that gets us to the correct handler. Let's talk about performance. Zone walker carries out one comparison at each zone. The zone depth is a constant in most common programs. Therefore, each zone walk incurs a cost of a small constant. About the correctness of zone walk, well, it relies on 2 important invariants. The runtime allocates stacks with monotonically increasing ID, and the lexical scoping of handlers and handler capabilities preserve the monotonicity, and thanks to this monotonicity, a single comparison determines the presence of a handler. We formalize the language and prove that the language with zone walk will find the correct handler, and we prove this with a simulation argument. As for evaluation, we implement a virtual continuation in Lexa runtime, a language that we own, and we call it multi-Lexa. We compare its performance with the base Lexa, which was published in UPSA 24. Base Lexa also implement stack switching and stack copying, But due to the lack of virtual continuation, it can only support a limited form of multi-shot continuations. The first question we ask is that, how much overhead does the additional bookkeeping in multi-lexa introduce? We collect a suite of benchmarks, and we run them on both base lexa and multi-lexa. And you can see that overhead is sometimes positive and sometimes negative. That is because base lexa also maintains some bookkeeping and allocation. So depending on the nature of the benchmark, the overhead is exercised either in base lexa or multi-lexa. But the takeaway from this experiment is that the overhead of zoning and zone work is not that significant. The second question we ask, does multi-lexa unlock significant speed up by enabling the parallel execution of multi-shot resumptions, which is not supported in any languages so far that support lexical handlers? We collect a suite of algorithms that can be easily parallelizable. And as we can see that as we increase number of threads, we do see a noticeable speed up. The different trends we are seeing here is due to the way how algorithm is implemented, not due to the language runtime. In conclusion, I've shown you the technique of stack switching and stack copying that are used to implement effect handlers and multi-shot continuations. And I show you why they're in conflict. In this talk, I introduce a novel technique called virtual continuation that makes these two techniques compatible and bring forward the full expressivity of effect handlers to the world. Thank you.
Questions? You said something about the MMU and physical memory, and it was a part you blurred out. I don't know if that's interesting to talk about.
Well, a little bit. So in the implementation, we actually utilize the fact that we own the entire virtual memory space, which is huge, that allows us to do the zonings.
Okay.
Mm-hmm.
You were saying that the lexical scoping of the effect handlers meant that your walking was sound. Do you avoid mutation or leaking the effect handlers so that they can't, because they could escape their lexical scope in that way?
Good question. So there are work already done that address this problem. Basically, the capabilities, the type system ensures that capability don't escape their scope.
Other questions? So it seemed like this builds on your prior work and it solves a problem in your prior work. Could you say more about the context of your overall work? Like what's next, either following on the improvements you made here, or what other improvements would you want to make to your overall body of work?
Right. So this work starts from the implementation of lexical effect handlers. We compile a high-level language lexical effect handler to assembly, right? And then we find that we can't support multi-shot continuation because of the problem I introduced here. And this paper brings back the full expressivity to the language.
So for this effect handlers, I guess you right now implement it in a specific language. Mm-hmm. Like say I want to do a similar thing in Haskell to have multi-shot continuations. Would I need to have compiler support for this, or would there be some way to implement this only in the Haskell runtime, or in the level as is, in language as is?
Well, good question. I'm not too familiar with Haskell ecosystem.
Any language, I guess,
yeah.
Not necessarily Haskell.
Well, I guess if you have the control of the compiler and the runtime, you can do that. For example, our work on UPSLA'24, how we use the stack address to represent the reference to the handlers are adopted by OxCaml. So I guess if you own the entire compiler pipeline, you can do something like this.
Okay. Yeah. Thank you.
Mm-hmm.
You said it was adopted by what? I didn't hear.
OxCaml.
Oh, okay.
Yeah, but they're still in experimenting mode, so I can speak for them.
Time for another question, if there is one. Oh.
Kind of a follow-up question. Do you think your approach can be implemented on top of WebAssembly, which only has stack switching?
Yeah, let's see. I mean, our implementation basically assume you have the control of a big memory space, right? I know WebAssembly have linear memory space, which might be tricky to do such things. However, our implementation is just one way of implementing the idea. Our formalism actually support many different ways of doing things. For example, we could implement virtual continuation using a nested list, right? We have a list denoting zones, and inside each element we have different lists denoting handler IDs. If you do indirections through that way, I guess it might be, have a fewer requirement for your runtime.
Thanks.
Thank you.
Thank you.